Just check the slides are moving.
Oh, okay. Yeah. এটাকে না আউট করা যাবে, এটাকে জাস্ট কেটে দিতে হবে।
এটাই কাটবে।
হ্যাঁ, স্টপ শেয়ার, না স্টপ শেয়ার করলেও হবে বলে।
এইটাই
হ্যাঁ, ওটাকে সরাই করো। Because it's coming somewhere from the middle. Have I stopped? No. Ah, okay. So let's see.
Yes, no.
And this one. Try to put it here. Yeah, I think this is totally reasonable. Okay, so all right. So I have to begin by thanking the organizers. It's lovely to be here for the very first time. The campus is beautiful. The food is nice. Meeting a lot of juniors and seniors. Also started feeling a little old by looking at, by seeing many like really youngsters. So okay, so what I'm going to talk today is some of the very recent work that we did. On the title is essentially, it's little long, and I'm sort of plan to briefly talk about two different but related works, but I may not have time, but let's see how far we can go. So the title is bipartite particle number fluctuation. So I'll explain what it means, and something called page curve. Now this page is the name of a scientist, so it's not the page that we think of. Page curve that appears in the context of entanglement entropy in so-called dephased lattice system. So I'll explain all of that, what they mean. But right away, when I say the word dephased, it essentially connects to the field of open quantum system, because there is a word called dephasing, which we all may heard of in some sense. So I have to briefly talk about open system. So essentially, it's a word related to open system and how do we understand certain concepts there. Okay. Yeah, okay. So very briefly, I think many of you know about what open quantum system is, but before that, of course, we have to talk about what a closed quantum system or absolute quantum system that we all study in quantum mechanics 1. It's a Schrodinger equation that gives us everything for pure state. That's what we do. But if you have a mixed state, you can also write an equivalent equation which carries almost similar information, and it's just given by a commutator for the density matrix. So that's for closed quantum system, which follows a unitary evolution. But in reality, of course, systems may not be closed. They are often interacting with the so-called environment or path, whatever you want to say. So your system of interest is coupled. It could extend energy, it could extend particles. So many things can happen in contact with the environment. And then, of course, a natural question you can ask is that what is the dynamics? So I know there is a Schrodinger dynamics for a closed system, but for open system, if I want to now describe this system as of interest, what could be its dynamics? So of course, it won't be a Schrodinger equation. In fact, the dynamics is no more unitary. So this probably one would naively expect. And the question is that what is the evolution? So you can actually, it's a difficult problem. There is not a universal answer to this question. And turns out, if you want to preserve some very basic physical properties, or if you impose some very basic constraint that you really want that your system to follow, then Lindblad actually long back derived a very general equation, which is written here. And often an open system is based in terms of a density of it, not in terms of pure state, because you don't have that kind of a notion. And that's essentially the Lindblad equation, which if you see, of course, this is the unitary part. This is what if you don't have any dissipation or anything, this part will be zero and you get a closed dynamics or unitary dynamics. And this is the part which takes care of the impact because of the environment. But this structure is extremely important. This is what actually preserves a lot of physical properties. For example, density matrix has to be positive, it has to be Cartesian, and so on and so forth. So many properties has to be obeyed for a physical system. So that restricts the structure, And this gamma is essentially mimics sort of the interaction state, how strong or weak your system interacts with the mass. And these L's are what we call sometimes called as jump operators. In a sense that if you have this kind of discrete system coupled with the environment, these L's, in some sense, you can think of like giving you excitation or sort of exciting the system between different levels. And that's the most general sort of in certain approximation you can think of as the most general equation, which is non-unitary. You can actually show that this evolution is non-unitary, and that's the equation. So when I say it's a system, what I would really actually consider is that this scale has a very specific structure. So I'll come to that, but this is a starting point of actually dealing with open system. That you, and it's actually quite a simple, if you have heard of Victor's law, in fact, it was primarily writing down linear equation because it's a local in time equation. A lot of simplification happens, but then of course you can go beyond this. Sometimes also Markovian because it's local in time, it doesn't remember the history. But then there is this non-Markovian equations which makes life even more challenging, and a lot of other things needs to brought in. But having said that, so we focus on linear master equation, local in time, and having that kind of master equation, then of course you can just solve for the density, having instant of time, and that's the same your system. And if you have that, then we know how to calculate whatever observable of interest. You can calculate, for example, current or anything for that matter, local density, if you have a lattice, anything for that matter, in principle, you should be able to calculate. But here, something important that we'll take sort of, I'll briefly mention, but we'll come back to that. Certain observables that if you look at are linear in rho. For example, if I'm calculating this O average, it's trace of O rho t. So rho is acting as a linear fashion. So that's fine, but then there are certain type of observables. If you say so, for example, alpha, on the other hand, is actually a nonlinear function of rho. So there is some cautious approach you have to take when you're going to calculate certain things. But just remember, take a note of this, that there are observables which will be linear in rho versus there are observables which will be non-linear in rho, and something might trouble you at some point, and we'll come back to that. Okay, so with that, let me do a very brief introduction of sort of open system. The first part, what I'm going to focus on, something called as bipartite particle number fluctuation. I'll tell you why I'm interested in this kind of problem. So it's just recently came on arXiv, and it was done in collaboration with Lokesh, who is a master student in IISER Pune, and Shubhajit and Devendra, who are, Shubhajit is a faculty in SRM University, and Devendra is a postdoc in ICTP. Okay, so sorry, how did you know Devendra? He was in IISER Bhopal, so we started some project, and that's how I sort of got to know him. Okay, so what is the motivation, or rather, what is the problem? So, problem is extremely simple. You consider any lattice, and let's for simplicity one-dimensional lattice, and you start feeding the lattice with certain number of particles, let's say electrons or fermionics. And you take some domain, you take some, let's say you make a partition, you take half and half, and then you ask what is the number fluctuation within this half part of the system. And I'll tell you one that is of interest. So essentially, it's a problem of quantum dynamics. So you want to essentially see that how these fluctuations doing as a function of time. The idea is to essentially see what kind of universality I can actually understand by looking at this kind of dynamics of number fluctuation. So the idea is to get certain universal features, and these are out of dynamics that we would like to understand. There are multiple reasons why I would look at particle number fluctuation. The reason is, often you can look at, for example, observables which are local. For example, in a lattice, you can look at local density. It's a local observable. Turns out, if you look at local observables, how they behave as a function of time and what eventually they do, at least a long time you can often predict by age, eigenstate thermalization, and so on, for theoretical system. But if you have so-called non-local observables, meaning you are looking at some observable which are not which are involved in science, which are let's say in your lattice, could be order of system science. If you're looking at those kind of non-local observables, the dynamics itself will be very different, and long-time prediction may or may not follow equation. So it's not really very obvious, and often the dynamics are very different than how local observables do. So local observable, for example, can relax very quickly, but non-local observable can have a very different dynamics. And the question is that how do I essentially understand now what kind of non-local observable I can think of? And the first observable, or sort of a very reasonable observable that you can actually come up with, is actually number. So so as I said, bipartite, essentially you divide the system. It need not to be half-half, but let's say it's a half. And it's an important observable. I'll tell you why. And you just define this one. So this is the content I'm going to focus, which is nothing but counting how many particles at any instant of time you have within the L/2 systems, right? Your full lattice is L. Within L/2, you are essentially looking at the variance of total number within the system. So that's essentially, so this L is a quantum operator, which is counting how many particles you have within this, and you're just looking at its variance as a function of time. And of course, you have to give some initial state. I'll tell you what that is, but this is the very simple question and how this essentially what it does as a function of time. So, and can I how do I choose L/2? Okay, so it doesn't really matter. Eventually, it will not matter, but what we typically take is, let's say, first left half. But it doesn't really matter.
But they are consecutive.
There?
Consecutive.
Yeah.
You said it more than.
No. It's a continuous. You literally choose the domain in a particular fashion. Yeah, so I'm thinking literally quantity lattice, like what when theta was situating some kind of quantity lattice, and I just do a bipartition. And then I look at ask what is the number fluctuation within that domain. Why it is of interest? Multiple reasons, but one primary reason is that many times, at least so-called free fermionic system, non-interacting systems, entanglement entropy and number fluctuation often related. So there is a huge interest of really knowing what number fluctuation means, because it might just directly hand over entanglement entropy, which is very difficult to measure because it's roll of row. You have to know the full state and so on. So it's very non-trivial, and it's quite expected because if it's a free fermion, the density operator just can be written in terms of 2-point correlation. The number fluctuation also can be written in terms of 2-point correlation. So you might expect that things would be related. Now, why it is non-local observable? I hope this is clear, because when you're going to do a square, it will involve Nij, which an Ij can go to any side to any side. That's the non-local observable. Okay, so again, just to repeat, I'm having some one-dimensional lattice, and in this work we essentially focus on a lattice which has a long-range hopping. So I'll explain the Hamiltonian, but so maybe even explain the image. So it's a 1D lattice. It doesn't only have nearest neighbor hopping, but it also can have a long-range hopping, meaning this side can talk to that side. But the long-range hopping is decaying as a power law with the distance. So Ing of the different signs is decaying as a power law. What you read as alpha eventually become mu in this slide. So it's actually a mu because alpha I have to keep for something else, and it's an exponent. So it's some long-range power law hopping decay exponent. So that's the lattice. And I said it's a closed system, but now what I do is I study an open system version, and why I do that, of course, I'll also explain. But these are something is like an environment the system is talking. In that sense, it becomes open. Now you bipartite and give some initial condition and essentially ask what is the number classification means. So that's what's the dynamics. Is the the question is actually quite simple to ask.
Long-range hopping is essential.
No, so you can so people are studying. Yeah, people are studying short-range, so no, so I'll tell you why exactly we are doing long range, but yeah, so because it has some reach physics, so but yeah, short range. In fact, there was a recent paper, actually that paper is also here, so I'll tell you why we are motivated to do long range. Yeah, so what is the dynamics? So it turns out in most cases, such dynamics going to follow some nice scaling. There is some nice universal property that you may expect. And this scaling, in a dynamical sense, is known as FV scaling, the Family-Vicsek dynamical scaling. It's a little involved, but I'll try to explain. So, turns out this number fluctuation is going to have such a scaling respect to system size and time. It's a function of two variables, A and B. System size is the time. So this is what you could expect. And this F is some function which you don't know. This is connected to your
Time is just with the dynamics.
time. So you have some initial state.
Stationary.
You have some initial state, and up to that state, you can think of that state is evolving under within time. It's evolving with the Markovian dynamics. And now I just take that operator and compute the expectation. So that state is not an eigenstate of the new variance, so of course it will evolve and it will do a non-trivial dynamics, and you just want to look at what happens. No, so this actually expected you should expect this to emerge for any things. As long as the system is not localized and all that. I mean, if it is chaotic and all, you should expect this kind of scaling to emerge.
And if I will it's a nearest step I want to
Exactly. So in fact, nearest neighbor could be probably z equal to 1. 1 is to I think it's 1. No, it's 2. There is 2. So let's say so because it's talking about like some kind of scaling of ultimately what is happening. I mean, you're see, okay, so think about this situation. I take this lattice and I just fill the first half. Fill first half of the lattice. I just fill in the elements. Okay. So another one is empty, and I take any half. So they have to leave. So essentially the number fluctuation initially was zero because we divided in eigenstate of the number of it. So the variance, the numbers are equal to 0. But now as the time is happening, the particle will start to go to the other side and there will be fluctuations. They will grow. But eventually for that kind of initial state, what will happen? Like, the other side is, let's say, very kind of initially, all these particles start to move out. So again, it can become 0. So it really depends on initial state, but so you expect some growth and so on for the number fluctuation. Okay, so this F function is some unknown function, but you know what should do when this P by LZ, which I am calling Y, if it is in the much smaller than 1 and much greater than 1, you expect some form of it. So in summary, so there are 3 exponents. Let's remember there are 3 exponents, very much like what Devraj was showing for steady state in some sense. So here I'm showing dynamically. So you have 3 exponents, alpha, Z, and then there is this beta. But these 3 exponents, I'll actually come to that. So just remind me, it doesn't get clear. So, so there are 3 exponents, but turns out these 3 exponents are not independent. There is a strict relation obeyed by this 3 relation, 3 exponents, alpha, beta, Z. And the most important that these 3 exponents defines a universality class. So if it is a long range, maybe there is some universality class. If it is a short range, it could be something else. But now look at here. This is the central. In fact, you expect this kind of behavior of number fluctuation in general. So very short time, you expect some growth with some exponent beta. Okay, and typically you expect that in the very initial time that growth should be independent of system size. So that's why you get something entirely on time. And then at a very long time, you expect, because it's a finite size system, you expect it to settle somewhere and it should saturate. Turns out that saturation should just depend on the system size. So alpha, if I take alpha, which is alpha is 1 in some sense. And after this though they start to saturate, there is a saturation time scale also I can think of. That depends on Z. So there is an alpha coming from here, beta coming from here, and Z coming from here. So if you look at now this collapse, if you scale your y-axis by a raised to alpha, it actually collapses this two. And if you scale your x-axis by L raised to Z, it will collapse this saturation wave, and as a result, you just get a perfect collapse, and that sort of indicates that that's. So this is sort of you expect, but you don't know what universality class your model could be in. So that's something that you need to figure out.
It's due to Z.
Basically,
The Z.
in the Z. Well, you have two independent exponents. You have to find. Okay, if you
Ratio.
you have to find two. So then the third gets immediately fixed. Okay, so what are the known results? Why we started doing long range? Known results in the last couple of years, people started, of course, first doing for free system, isolated system, and free formula and so on. And of course, isolated free, you expect a ballistic universality class, and it becomes 1, 1, 1 alpha 1, Z1. There are a lot of nice works done in this direction, and then it was also extended for many system like Bose-Hubbard or various kind of interacting systems, which shows different exponents and so on. But so there was a lot of nice work for the isolated system where one showed that those kind of scaling emerges for number fluctuation. And then very recently there have been attempts to understand whether you see the similar emergence of this kind of scaling for open systems. And very recently it was done for actually, so this work was the first one for open system where they did a short range model and had a complete numerical sort of an approach to show what happens. And they found that the short range under dephasing, I'll exactly tell you what dephasing means, and they saw that it becomes diffuse. So it becomes a diffusive universality class with this. So these exponents, if you think a little bit, you can actually, so for example, mean square displacement goes as c raised to half. This beta is sort of taking over that half that is sitting there and so on. So so that was the kind of status of the field, and it was a purely numerical. So what was, if anything is diffusive, you sort of think that there is some analytical thing that we can probably give. So that was our motivation. But more than that, we then thought, okay, let's try a slightly richer version of the model, which is long range. And why long range is richer, I thought of putting one slide, but I didn't finally able to put. Long range systems actually offer different phases. I think this will become much more clear. Yeah, I will not motivate much why long range is interesting. And of course, there is also people can actually realize in extent. So it's not a purely theoretical construction. So lattice is very simple. It's a non-interactive lattice. Just having a power law decaying. So this di is basically I minus j raised to k. The mu is mu. Remember, mu is a very important parameter, which is the Hawking exponent. Long. So if you take mu tends to infinity, you get a type. You get the standard nearest neighbor lattice model.
People figure out the paths.
Yeah. So what I'm doing is that for this exactly. So now I'm coming to that. So this is just the lattice part with the Hawking. What about this? Like we call it dephasing, which is one form of one way the system interacts with the environment. So that I modeled through a linear equation, and earlier you remember you saw something L. But now those L's I write as N's. What is Nj? So these are like local each side particle number. Okay. So N0, so this is what it is doing. Why it's called dephasing? In a sense that it's keeping whatever number of particles being put in the system, it conserves that number of particles. Because it is finally it commutes. Right. So particle number is conserved. So if you think of the density matrix in the fog basis, what this kind of interaction is going to do is to kill those coherences that gets developed in the fog basis. In that sense, it's a dephasing. It's killing those phase relations. So that's why it's called a dephasing sort of jump operators, if you like. Yeah, so I hope this is clear that this is this H long range model under dephasing. And this is the simplest equation that you can have. And now the question is that what happens to number fluctuation? Yeah, what happens to number fluctuation? I still haven't said what is the initial condition. We'll come there. But now, very simply, of course, number operator is a 2-point correlator. If you look at fluctuation, it involves 4. So number fluctuation at the end you can write in terms of 2 and 4. Now, if you have a non-interacting system, of course, 4 point you can break it into 2 points, product of 2 points because you have Weeks theorem. So then life becomes much more simpler. But now in this problem, you don't have Weeks theorem because look at here, it is the Hamiltonian is quadratic, but look at here, it's a quadratic 4. So you can't really have Weeks theorem in general. So you have to evaluate 2 point and 4 point independent, and usually 4 point is a very non-trivial quantity to calculate. Yeah. So the information of bath is precisely coming through this. This is what I'm modeling. So this part is essentially telling you a system is not isolated, because otherwise this would have been the dynamics. Because the system is talking with the environment with in some way. I'm actually modeling that information is close to the no. So that's a good question. No. So this is the lattice. Half is what my observable. I'm looking at something in this half. But this as a whole is my isolated system. That is this age. This age goes over the entire. But I'm looking at the L by 2. That is my what I want to look at. But this is the full lattice. And this is the environment that I'm modeling. In some sense. So basically, in order to at least if my focus is here, I need to solve 2.4. Yeah, but 4 point is very important. So, but look at how this model becomes quite interesting. That's essentially the next slide. So, as I said, the linear dynamics involves squatting operators, so you can't expect Wick's theorem. And there is always, in fact, bigger problem that happens when you have many-body interaction. You look at any 2 point or 3 point or 4 point equation of motion, it involves hierarchy. So usually there is this leadership kind of hierarchy that happens, right? And then you have to truncate, and then things can go out of hand. But it's very nice thing that happens, at least for this equation of motion. You can actually show any endpoint equation of motion you look at, it closes to me. So that's the beauty. But still, the thing is non-Gaussian. But yeah, so if you look at, for example, 2 point equation, it involves this 2 point. It means that 4 point, it can even lower out. So that's
Your cover is constant.
sorry.
Your cover is constant.
Common sense. So if I'm arguing, so now
I worry about any because there's a confident in a view. And the number the decay is not tied to dependent. So I have got fixed point. So we usually go to that.
yeah, so if you solve for these dynamics and ask what is the long time limit of the state, it's actually the maximally mixed state. It's actually the infinite temperature suggestion. But any initial state you take it in eventually go there. Yeah. So what is it? So
you must get in average set initial conditions. So
no,
asking like how it is naturally.
no, but the state will go there. See to be state at that time, I think I remember the time.
Yeah. Like
It's not the dynamics. I mean, interesting dynamics. So the steady state could be a little boring, but the dynamics could be very rich. So, once again, I just want to mention that just because 4 point closes in 4 point doesn't mean that you have a Gaussian field. But you have to still calculate it independently. But the good thing is that you can take a deep breath and okay, got closed. So that's one positive side of it. You can ask why that happened, and the brief answer is that this operator being Hermitian. You can actually show any Hermitian operator you put there, this property holds. Yeah. Okay, but still, as Sudesh said, 4 point is a difficult quantity to calculate. So we have to take at least some simplified, we have to go to some simple region where I will expect some simplification. So what we do is take something called a strong dephasing. So strong dephasing gamma, which was the parameter that takes care of sort of telling you how system is interacting with the bar. So I take that to be the strongest parameter in the problem compared to the Hawking. So that's we call strong dephasing limit. Why it will become clear. Turns out, so if you think of 2 point correlators, so you can think of this as a matrix. M and N goes from one way, it's actually a matrix. If you take strong dephasing, you can actually show very nicely that all off diagonals very quickly decay. Very quickly they sort of decay, and the entire dynamics can just be described in terms of diagonals. Okay, so and you can ask what is that dynamics? What are these diagonals? So essentially, I'm getting rid of all the off diagonals, and you can actually show that they don't contribute. So there is an effective dynamics that comes out just for the dynamics, which there for the diagonals, which for 2 point correlator is nothing but the local populations. So your local population. So this kind of in fact, if you now ask what is happening for the state, It's actually becoming like a cluster.
Yes,
Because satisfying of all. Absolutely. Absolutely. So, so now, if you look at the population is coupled to population, and in fact, if you find it a little hard to see, if you take mu tends to infinity, this is literally a diffusion equation on a lattice. With this being the diffusion constant. So, so this is an effective diffusion constant that you now, which is emerging from this calculation. So this is fair enough. But this is not it because you now have to take even the 4 point. Okay, so this is just one very simple sort of. So you can look at how does this 2-point correlator or the local density relaxes. But then I have to give you initial condition. So primarily I'm going to talk about the initial condition, which is you can call it charge density wave or you can call it alternate initial condition. It's very simple. You basically prepare the lattice one particle, no particle, one particle, no particle. That's what you call alternate initial condition. So we should then give it from here. If you take that as an initial condition and ask in any particular site, whether it's a 0 point. So here in this case, I'm looking at a site where there is one particle initially, and it should eventually go to half. That because ultimately at a long time it should become homogeneous. There is no reason it should not. So it goes from 1 to half, and it actually relaxes in a time scale 1 by lambda, where lambda was the diffusion constant.
It doesn't, right?
So yeah, in fact, there is a very weak dependence on me. It's a very weak dependence. Yeah, so in here there is no dependence on mu. But note that even on top of that, the time scale doesn't also depend on system size or anything. It's sweetly relaxed. So just keep a note of that. So this is the just a 2-point.
The time scale does not differ because you have infinite difference.
So just to answer that, so this is basically initial value. If I take the so-called domain one initial value, so say the first half is filled, the other half is empty. And now if I look at local density, it will actually depend on. So that answer will actually scale. So it very much depends on initial. Okay, so now what about the 4-point? Very nice, right? Extremely missing. But again, if you take strong dephasing, turns out in this language, so in principle we have 4 indices, M and PQ. But if you take strong this thing, I mean, it becomes MN, which is again a diagonal. In some sense, it's also even the diagonal elements that contributes. It's quite messy. Now the question is that how do you solve this? Well, you can numerically solve it, of course, but it's quite expensive in a sense. So first, if you look at just without the strong dephasing, let's say you start from that nuclear equation, you don't impose strong dephasing, which makes it diagonal. If you don't impose that, and if you try to solve 4-point, it actually you have to solve the matrix L4 cross L4. And remember, any problem if you want to look at all these exponents, you typically want to go to large system size and so on to clearly extract these scaling exponents. So L4 problem is like you can't really go to very large system size. When you take strong dephasing, which is this equation, this actually reduces to L squared plus L squared, which is still difficult. It still makes it. Remember, for 2-point, it was actually L by L, but dealing with L plus L matrix. But here, because it's a 2 indices, it becomes even expressed by L squared. But it's still non-trivial to go to large system sizes. Yeah, so this, yeah, we start from equation and slowly take strong dephasing and see how diagonals are clean and then you get this. So this is the analytical part, which and you can expect over what are these functions because these are like taking care. These are fermions. These are taking care of the Fermi sets. For example, if you have n equal to n, this should be 0.
Yes.
Because the C dagger square is 0.
Is capital gamma.
Capital gamma was the diffusion constant. So if you go back, I defined it here.
Yeah.
Oh, sorry. You made this one.
Yeah, yes.
So this is the effective. So what is happening? You have bunch of these particles in the lattice, and they're diffused. They're essentially being a diffusive. And what is the diffusion constant? What a natural time, a natural scale that emerges is essentially this. Okay, so then what happens? So even at this level, things were not clear. So what we found is that if you give the initial state, which respects translational symmetry, then there is a representation that I can put up where life becomes extremely simple, and I can actually reduce the problem for 4 quantum actually to a L by L problem, and my numerics will be extremely efficient. So what do I mean by translation invariant of the initial state? Meaning, for example, if given any chances, for example, alternate state. Okay, so okay, I won't touch page curve. So yeah, so basically, for example, alternating state would be a translation invariant state. So if you give me those kind of state, then you can actually, if you carefully think, this entry F, M and Mn, you can actually think of a distance M minus N mod as a distance, and you can actually show any M and N you choose, but picking P phase, they all will be same because of the theoreticity of the thing. So that essentially now become a one variable problem. So then you can actually write a very nice equation, very much like a diffusion equation, but now for a 4-point correlator, written in terms of a single variable. Very much it looks like a diffusion equation again, but slightly different. And it becomes an order L by L problem. And again, you see somehow it's again a kind of diffusion equation with diffusion constants keep coming here. And this let's not get into it. I mean, one can actually get it. Okay, so just to show you, for example, if you compare with the exact equation and this representation, and this slide is just showing that they perfectly match. Then in a strong dephasing. So if I take strong dephasing, then of course this, I went from exact to bond length representation. This is just showing you that there is nothing wrong in your calculation. So, but no more, not much details beyond that. Okay, so now let's come to, so now you have figured out a way to calculate and so on in the strong dephasing. And you are asking what happens to the number fluctuation. That was the aim. So before going to the growth, you can actually ask, how does the number, say eventually it will saturate. Eventually it will saturate, and you can ask, how does it saturate? So you expect, since it's a Lindblad equation, you expect things to saturate exponentially. Okay, so it will saturate in an exponential fashion. So it will approach to the steady state in an exponential fashion with some time scale given by the star. So as you see this delta, which is essentially again telling you how it approaches to steady state, is in a log scale, it's a linear, so it's actually happening exponentially. And if you plot this time scale, how this time scale is varying with L system size. So you look at this one. So this one is for mu 1.7. It actually went as L squared. Whereas if mu is 1.1, in fact, even 1.7 or infinity, it's like a time binding, it's actually L squared. But if mu is 1.2 less, it's actually a very different power, which is 1.4. So this so-called saturation time scale going as L raised to Z, where Z is depends on mu. So yeah, okay, so that's one thing. And if you now plot this Z versus mu, what you see is that in fact after 1.5, so mu was what? The long range exponent. Okay. So if you take mu greater than 1.5, it very much behaves like a short range exponent. Why? Because this is the class which is diffuse. So this is very much like behaving like a diffusive dynamics. And if mu less than 1.5, the Z exponent is going as 2e minus 1, and which if you think a little bit, it actually becomes a super diffuse. So you can use so mu greater than 1.5, any value you take for mu greater than 1.5, this limit is right. No. So in some cases, it's 3 and there is a factor of half that you have to take here, not 2. Either 1.5 or 3, you will see that actually how you write your factor of 2 can be. And in fact, if you know entanglement interval literature, this is exactly what the measurement is based on. Nicely one. So okay, so essentially the normal model has given you a crossover from a super diffusive to diffusive region. So when mu is very small, it's like the long range is very much activated. You start to see a super diffusive behavior, and then it goes to diffusive at 1.5. And if you remember my second or third slide, where I was the scaling, this is precisely how number fluctuation goes, and this is a collapsed version of it. If you scale y-axis by m raised to alpha and x-axis by lz, then nicely collapse, and you can get all the exponents. And you can verify that these exponents precisely if mu less than 1.5 are super. So that's verified. So I think I should end. I should not go to the second part. So just to summarize, I mean, if you look at the particle number fluctuation or bipartite fluctuation in lattice systems which are open, I mean, again, you do expect a scaling, and we show that they emerge. For long range, of course, it has a crossover, very nice crossover from super diffusive to diffusive. The another thing that I couldn't show, and I also don't want to show you in the calculation, you can actually extract this exponent also analytically, at least for diffuse. We couldn't do it for super diffusive, but analytically, you very nicely able to show all these exponents alpha, beta, and z. Very nicely analytically, you can extract and prove that indeed it's a diffusive. And the reason is that underlying there is some Gaussian properties that you have to bring in. And as I said, there is a crossover with this. Okay, so I think I should. Yeah. Okay. Thanks.
If you have some quick question, then ask, but we have a key break here. Question. And he's here until 9. So he will designate environmental secretary online. So you catch him for the next time. So yeah, we will take a quick break and then we'll get now to online blocks. So we have 2 during online blocks.
Thank you.
Yes.